The Hall position sensor is made for magnetic field sensor according to the Hall effect. The Hall effect is a type of magnetoelectric effect, which was discovered by Hall in 1879 while studying the conductive mechanism of metals. Subsequently, it was found that semiconductors and conductive fluids also exhibit this phenomenon, and the Hall effect of semiconductors is much stronger than that of metals. Utilizing this effect, various Hall elements are widely used in industrial automation, detection, and information processing. In this lesson, we mainly study the Hall effect and Hall sensors. First, let's learn the Hall effect. A static current-carrying conductor is placed in a magnetic field. When the direction of current is inconsistent with that of magnetic field, electromotive force is generated between two planes parallel to the direction of current and magnetic field on the current-carrying conductor. Such phenomenon is called the Hall effect, and the force is called Hall electromotive force. A current-conducting plate is placed perpendicularly to the external magnetic field wall and supplied with current in the direction shown in the figure. Each electron is subjected to Lorentz force, and the magnitude is Fm equals eBV, where E is the electron charge, V represent the average velocity of electron motion, and B refers to the magnetic induction intensity of the magnetic field. In the diagram demonstrating the Hall effect, Fm go upward, and electrons drift downwards under the affection of Fm. In this way, electrons are accumulated on the upper side of the plate and positive charges are accumulated on the bottom side, thus forming an additional internal electric field E, which is called the Hall field. The electric field strength is A equals A over B, where A refers to the voltage. Electrons moving directionally within the Hall field are not only affected by Lorentz force, but also by the Hall field itself. Its magnitude is EH, opposite to Lorentz force. It prevents charge from accumulating continuously. When the Lorentz force and the Hall field force acting on electrons are equal in magnitude and opposite in direction, that is, EH equals EVB, then EH equals VB. Next, we will cover how a Hall position sensor works. The working principle of a Hall position sensor is shown in the figure. The Hall element is placed in a magnetic field, and two permanent magnets with the same magnetic field strength are placed on both sides, which are opposite to each other in the same polarity. The magnetic induction strength in the middle of the magnets B is equal to 0, so the Hall voltage UH output by the Hall element is also equal to 0, and the displacement X is equal to 0. When the Hall element moves between two magnets, the magnetic induction intensity sensed by the Hall element also changes. At this time, U is not equal to 0, and its value reflects the change of relative position between the Hall element and the magnet. Finally, let's learn the applications of other Hall sensors. Let's first look at the commonly used Hall sensor UGN3040 and its application. UGN3040 is a common Hall sensor. Its appearance and principle are shown in the figure, and the voltage of circuit current of it can range from 4.5 V to 24 V. The first is the Hall proximity switch circuit, which is non-contact and magnetically controlled. When the magnet approaches, the switch is turned on, and when the magnet leaves, the switch is turned off. The second is the Hall effect tachymetric transducer. The figure shows several Hall effect tachymetric transducer with different structures. Connect the input axis of the turntable with the revolving shaft to be measured, and when the revolving shaft rotates, the turntable rotates accordingly. The Hall sensor fixed near the turntable can generate a corresponding pulse when each small magnet passes. Thus, by detecting the number of pulses per unit time, the speed can be measured. According to the number of small magnets on the magnetic turntable, the the distinguishability of the sensor measuring the rotation speed can be determined. As shown in the figure, it is a motor speed detection circuit, in which the Hall sensor UGN3040 is adopted. Connect its output with a low-power PNP transistor VT, so that B, the signal polarity of the output of VT, is inverse to A, the one of the output of UGN3040. So, the circuit can obtain A and B, two kinds of signals with opposite phases. The actual speed of the motor can be obtained by connecting A-B signal to the tachometer. The third is steel ball counting. The Hall switch sensor SL3501 has high sensitivity integrated Hall element, in which very small magnetic field change can be detected, so the sensor is used for counting metal parts. The figure shows how steel balls work and demonstrates its circuit. When the steel balls pass through the Hall switch sensor, the sensor releases a negative pulse voltage with a peak of 20 MV. After the voltage is amplified by the operational amplifier MU-A741, the driving transistor VT2N5812 works. The VT output can be connected with a counter for counting, and the count value can be showed by the display. In this lesson, we have learned about the Hall effect, the operation of Hall position sensors, and the applications of other types of Hall sensors. You can look up the materials after class to find out which Hall sensors are applied in life and production besides that mentioned in class. That's all for this lesson. See you next time.